All right, guys. So here is part B of the linear regression video. Now, here again, here's the results. We have them right here. When you run the summary command, let me just erase this and do it again. All right, here you go. Right, when we run the summary command, here it's giving us basically a summary of the analysis it gave us. Now, again, the residuals is giving you the breakdown, the 5-number summary of the residuals right here. The coefficients, the estimated coefficients, right? This is the intercept. This is the coefficient for our actual marketing total, and we just talked about what does that mean in terms of actual business talk and business speak, right? That if we spent no money on marketing, we would see a revenue of $32,000. For every $1,000 we increase in our marketing, we add to $51.92 in the revenue, right? What does all this stuff mean here? Right? Again, this should be all review for you guys, right? So, let's see if I talk about it here. I don't talk about it here. So let me just quickly go over this. Standard error. What is standard error? Okay. Standard error is basically the standard deviation of the results when you were calculating the estimates. The larger it is, the more imprecise it was. The smaller it is, the more precise it was. Okay, that's basically it. The standard error, because again, these are estimates. So the standard error is basically the standard deviation for each one of these estimates. Okay, that's pretty straightforward. Now, here is where we enter crazy town. What is t-value? All right. Again, this is meant to be a review. Here is, let's just do this, right? Here is the t-distribution, right? It looks like a normal distribution. See that? And you'll see that you have various different kinds of t-distributions depending on something called degrees of freedom, right? Now, what is that? All right, this is all advanced statistics stuff. But anyway, the whole point of a t-value is, well, first of all, how do we calculate the t-value? It's simply going to be the estimate divided by its standard error, right? Or standard deviations of the values, right? This divided by that will give you a p-value. We can confirm that right here. If I take my estimate right here, my intercept, let's do it for the coefficient. Right, there's my coefficient value. I divide it by its standard error or standard deviation of values. And look what I get. All right, I get this value right here. That is my t-value. Now, what is a t-value? And how is it related to this? Well, the t-value basically, in the context of linear regression, right? I won't get too much into t-value because this could be a whole stats lesson. But the t-value basically is measuring to see, okay, based on the actual estimated value and based on the standard deviation, right? It's basically trying to calculate the score t-values basically tells you, hey, how random was this value based on its error, okay? The larger the t-value, the further it is away from the center, right, from the center, and the more likely that this value is, we got this value not based on some random noise. Okay, any time in the world of statistics you're crunching any estimate, remember that estimate is always based on samples. Inherently, because it's based on samples, there's some sort of error around that estimate. It's not always about the estimate, it's about the distribution of the estimate. Okay, so it's always going to assume that a total random model, that if we took data that was completely random and there was no relationship between the independent and dependent variable, we'll still get some sort of score, right? But that score will be based on just random noise, right? It'll be just based on some random errors or random noise, and it'll have a t-value that's fairly around the middle over here. It'll have a small t-value. And that small t-value basically represents the fact that, hey, yeah, I know you got some sort of value, but that value was based off some sort of random noise, right? It's really not what we call statistically significant. And in the world of statistics, you'll always hear this. It's not statistically significant, okay? This t-value, both of these t-values, one has a score of 50.36, one has a score of 21. This will put you fairly outside these graphs, like all the way to out here in the outliers, all the way out here in these outliers, right? And because they're so far away, what that means is these values right here, their numbers are so, their numbers in conjunction with their standard errors, they're so unique, right? They're so unique that they couldn't possibly be generated by some sort of random noise. It is a value that's actually very significant than what we would normally see if it was just a random value. It is statistically significant, right? Once again, let's say hypothetically the estimate here we had a small estimate here, and let's say we had a standard error that was basically the same value. It was the same value, right? Your t-value would basically be what? It would be 1 at that point. It would be 1. Because for whatever estimate value you got, your standard error is the same size, okay? That translates into a t-value of 1. That t-value of 1 would be right here, right? Not very far from, obviously not very far from 0. It's right here in the main space of the t-value. That's basically saying, hey, you know what? Look, there was so much error and noise. There was so much deviations. The deviations were so large, or the amount of errors in that data in calculating that value was so large that this value basically is just by hapstance. It's not something statistically significant. This coefficient is not giving you an accurate value of any kind. It's not giving you any meaningful value of any substance in your model. But because of the fact that the standard errors relative to their values were actually very low, which obviously created higher t-values, those t-values put you way outside the scale. And that signifies, listen, to get a t-value like that, right, there's something outside of random noise generating that value. Therefore, these values are indeed statistically significant, and there's something to these values, right? We should pay attention to this relationship, the statistical relationship between these values. There's something here. All right? And obviously, in conjunction with the t-value, this PR greater than absolute value of t, what is this basically saying? This is basically something called your p-value, right? Your p-value. This is basically saying, okay, wherever your t-value is on this line, right? Whatever the tail value to, like, let's say hypothetically your t-value is over here, right? That p-value is always measuring the space to the right, in this case, if it's positive, to the right of the t-value. So basically whatever that tail value is after here, right? And if that p-value is, or what we call probability value, basically probability value, right? If that p-value is larger than 0.05, there's a reason I'm saying 0.05, but larger than 0.0, for example, 0.05, then it's going to be somewhere around here. If it's less than 0.05, then it's going to be out here in this tail, right? And that basically signifies, hey, it's really far in the tails, or it's out here in the main space, right? That p-value. Because obviously, look, the further inside you get, what's the p-value right here in the center? It's 50%. If you slice the graph in half, it's 50% this side, 50% this side. As you move over this way, to the right, to the right of this line as I keep moving, this vertical line as I keep moving, the probability of the space to the right of it gets smaller, smaller, and smaller, okay? So when you have a t-value of any value, it's basically begging the question, okay, well, if you plot that t-value on this x-axis, what's the probability of the space to the right of it? What's the probability of the space to the right of it? And obviously, if it's something less than 0.05 or 5%, then it's something extremely rare, and that re-emphasizes the fact that, hey, you know what? This is a statistically significant value, right? Now, why 0.05? You guys remember your confidence intervals from stats? 90% confidence interval, 95% confidence interval, 99.5% confidence interval, right? 99% confidence interval, right? That's basically why I said 0.05. 0.05 basically will, I'm emphasizing the fact an alpha of what we call 0.05 or 0.025. And anything greater than that, right? Anything less than that value is basically saying, oh, okay, cool, you're out in the tails. Anything greater than that, saying, oh, okay, you're out in this area. Because remember, whenever we measure things, we always measure them within the concept of confidence intervals, right? Again, that should be a review. We'll talk about that in a moment, a little bit later. All right, so that's basically what's happening here. This is basically measuring the probability of the tail, the probability of the tail at any moment on the x-axis of the t-value. And it's doing for both of them, right? And here it's giving the significant codes. We can ignore that for now. And then down here, we're talking about, we have some more stats. Residual standard error. This is the residual standard error on the whole model, right? The residual standard error on the whole model. And basically what it does is it measures the average of the squares of the errors, right? The average of the squares of the errors. And the lower the values, obviously, the closer it is to zero, the better the fit of the model, right? And what is this 170 degrees of freedom? Okay, 170 degrees of freedom basically is another concept in stats when you're measuring different measures and different models. Okay, you plug that into your, as part of your analysis as we're doing, like we saw this before over here, degrees of freedom as well. Okay, so what is degrees of freedom basically getting at in terms of plain speak in stats? All right, so degrees of freedom for our analysis is 170, right? Why was it 170? Well, let's start off with the formula first. How many rows did we have in advert? We had 172 rows of data. Okay. The formula for degrees of freedom is basically the rows of data you're using to make your linear regression model minus the predictors, basically minus the amount of independent variables you have. We have one independent variable, marketing total, okay, minus 1, which represents the intercept. Some people make this, I've had some students in the past make this mistake where they take the number of data, the number of rows of data, and they subtract 1 from it just for the intercept. No, 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 no. I mean, I'm sorry, just for marketing total. No, no, no. It's the rows of data minus the amount of independent variables we're using. In this case, it's 1. And then another minus 1 for the intercept. So if in our example, that becomes minus 1, minus 1. So minus 2. 172 minus 2 is 170. All right? That's how you technically calculate degrees of freedom. But what is degrees of freedom in the times of statistics? Well, the degrees of freedom basically means how many of your data points were free to be independent. They were free to be any value you wanted them to be, right? What does this mean? A smaller example that's probably easier to understand is, let's say, hypothetically, I told you, give me 4 numbers that averages 10. Okay, give me any 4 numbers that averages 10. You'll choose any number. You'll choose any value for the first value, any value for the second value, any value for the third value. But the fourth value, that fourth value has to be a specific number based on the first 3 numbers, so that all 4 numbers average 10. Therefore, that analysis had 3, even though there's 4 values, it only had 3 degrees of freedom, because only 3 of those numbers could be any number they want. That last 4th number had to be something specific. Same thing with our analysis right here. The intercept and marketing total, they weren't free to be whatever they wanted to be. They had to be something specific so that, right, I'm sorry, the last 2 values of our data, our rows of data, so that we had a certain intercept and marketing total given all the other data, right? And which one is kind of irrelevant. But the reality is that 2 of those values had to be something specific so this analysis worked. Same thing with our example. If you take 4 numbers and give me the average of 10, the first 3 can be anything you want. That 4th number has to be something very specific so that the whole thing ties in together and gets an average of 10. That's why degrees of freedom, right? And that's why for every independent variable you have, your degrees of freedom keeps going down. It keeps going down, all right? Because there's going to be more limitations on the data to get a coherent result. Okay. R squared and adjusted R squared. Let's talk about that a little later. F statistic also with the 1 and 1 degrees of freedom. I like to talk about that a little bit later. So let's save that for a little bit later. Right, these basic ones. That again is a review. I just wanted you guys to review this. Now back to the t-values real quick. The t-values, right? When you're building your model, let's say here we just have one independent variable. But if you have many independent variables and you're trying to decide the most optimal model, you're always looking at that t-value. Because you want to keep the t-values that are large, and you want to drop the t-values that are small that fail the p-value test, right? That basically fail the p-value test. So that's why the t-value is important in terms of building your model, figuring out which independent variables you should have. Right? And again, the R squared and the F statistic we'll talk about a little bit later. Let's moving right along. Okay, predicting outputs now. All right, predicting outputs. You can predict the outputs using the SLR model. This works best if you predict inputs inside the range of the existing model. I mean, the existing data. That's what I mean there. If you predict using inputs inside the data range of the existing data you use to make this model. That's what I mean. Revenues can only be predicted for values within the marketing total range of values, right? If I take a summary on the marketing total data, actually make it a little bit bigger so I can see it clearer. All right, here we go. I get a range of the values in marketing total. Here's my min, there's my max. That's it. Now if I want to do, again, remember, marketing total is my independent variable. Now if I want to do predictions using this model, linear regression model that I created, okay, I can only use values from this point to this point. Nothing outside that range. Why? Because when we made that model, we only use data within that range, right? We only use data within that range. So suppose we want to predict the revenues if we want to spend $460,000 in marketing, all right? $460,000 in marketing. First things first, the data does not have an input of 460, right? Let's look at that. The data does not have an input of 460. Let's first verify that, right? So let me find all the values of marketing total that are greater than 430. All right, 460. But first of all, do you realize how I converted the business question into my statistical question? I had to take the amount they're asking, how much money will we predict how much money revenue we'll generate if we spend $460,000 in marketing. I know my data when I train the models in the units of thousands. So I must divide this by 1,000 to use the input of 460. That's number one. Let me check to see if I had values of 460. Marketing total, anything greater than equal to 460, and just give me the marketing total column. Okay, I have only one value. I have nothing equal to 460, but I only have one value that's greater than 460, 481. All right? Okay? That's fine, right? In fact, let me take a small, here in this example, let me actually use this as an opportunity to take a smaller example. Let's take it greater than or equal to 430. All right? And here, as you can see, we have values of 435, 440, and 481. We don't have a 460 value. That's fine. That's fine, right? To go ahead and do the analysis, let me fix this. There we go. To go ahead and do this analysis, I'm going to use a function called predict.lm, right? And I simply give it the parameters of the model and the table of values that I want to predict. This is important. I need to give it a table of values that I want to predict. So I need to make a table based on these predictions right here. I'm sorry, not these predictions, but I'll do one right here. I'm going to predict 460, 465, and 470. That's basically what's going on. I want to predict all those values, not just 460. I'm predicting 465 and 470 as well. I'm just showing you that we can make multiple predictions at once. It just doesn't have to be one off, right? But that second parameter must be a table of values, okay? And obviously the here it's just a parameter. We're just saying predict the predict function. Hey, we just want a prediction based off this model right here, okay? So first things first, let's go ahead and create the table, right? And I'll call this table new rev. That's fine. Notice the name I choose, guys. Notice the name I'm choosing. It has to be the column as when we're doing the prediction. When we're doing the prediction, the table I give must have the same column name as the independent variables in the data in the table that I use to train the model. Because this model can only make predictions off a column called marketing total, underscore total. It'll be literally looking, when you give it this table, it'll be literally looking for this column named that. Because in this model, when it was made, the column that was predicting the values was marketing underscore total. That's why the names must be the same, right? And here I will give a sequence of values. Boom, I got my table. Just a simple table, 3 rows, 1 column, right? Now I can go ahead and call the predict model. And we can check out the results we get. That worked out pretty good. Boom. This is the results I get back. What's going on here? All right. All right. For the value of $460,000, if we spend $460,000 on marketing, we get an estimate revenue of $55,889. Again, the value comes back at 55. Remember the units, people. Please remember the units. So we get an amount of revenue back of $55,894. Again, seems kind of low to me, but that's a conversation for a different day. Now that that can't be an exact number, right? Obviously, it's an estimate. It's a linear regression. Everything in stats is an estimate. The numbers that stats give you, statistical analysis give you, are not the point. The distribution is the point. That is why, again, here's that confidence interval thing again. You are given a 95% confidence interval. Now, remember what confidence interval means. I briefly talked about it last slide, but what does confidence interval mean? Confidence interval does not mean that you're 95% confident that this is the value. No. Oh God, no. That's not what it means, okay? What the confidence interval is saying is that if you were to make 100 predictions using that data, using that linear model that was built off that data that we used, okay? If you made 100 predictions, all right, with the market total being 460, then 95 out of those 100 results would fall in between 50. Oh, this is a typo right here. Not 50, this is not 50.8.943. This should be 95 of the 100 results out of the 100 results that we ran would, of the population of the actual value, actually truly would be between 49.75 and 62.03. That's what 95% confidence interval is saying. That if we did this 100 times, then 95 times out of that 100, right, the actual value would fall in between, not this range, these ranges right here, these two ranges right here. Okay? That is what confidence interval is saying. That is basically saying, hey, 95% of the samples you run will truly be within this range, right? Will truly, even though you got this number, you're only going to see this number 95% of the times between this range. I'm sorry, not this number. I take that back, right? This number is actually irrelevant at this point. That if you ran this 95% of the times, if you do the prediction or you run the results, your prediction from based off your linear regression is going to give you a value between these two values 95% of the times. That's what it's saying. This range here is probably more important than these values when you're doing linear regression. The range is always more important when you're doing stats. Okay, and we can up this. If we wanted, okay, instead of 95%, if I want to know, if instead of knowing the range of values 95% of the time, right, what my prediction is going to be, I want to know my range for my prediction. That'll be 99% of the time what my value will be, right? What is the range of my predicted value going to be? Well, yeah, let me say it this way. What is the range of my predicted value going to be 99% of the time, right? And here we could just add another interval, another parameter, to our model called level. And here, see, by default, it's always 95% confidence interval. Everything usually tends to be, by default, 95% confidence interval. And now, this got cut off here, but we can see it clearly here. 99% of the time, given my linear regression model, if I spent $460,000 on revenue, on marketing, on my marketing total, on my marketing data, then 99% of the time, I will get some sort of revenue that is between $47,796 and $63,991. 99% of the time, I'll get some sort of value in between that. All right. And then obviously this is 465,000. This is 470,000, and you can see the values accordingly. Okay. That's what confidence interval means, and the distribution when you're doing measurements and estimates in any space, especially in the financial space, that distribution is critical. That distribution is important. That's why the results, the prediction, gives it to you in a 95% confidence interval, or whatever one you want to decide, but it gives you some sort of confidence interval of the results. It gives you a lower and upper bound. All right. Now, let's talk about confidence intervals a little bit more, right? Just so you guys completely understand this. Let's do a thought experiment, basically a thought experiment. Now, before MapReduce and Hadoop, right? And my MITA students, you guys should be messing around on your own with learning about MapReduce, Scala. Spark. All these guys. What my MBA students, what MapReduce, Hadoop, what the stuff is that in the world of the cloud, in the world of this massive data, we have distributed servers all over the place that not only store the data, but they also do processing on different sets of data. All right. Before we were able to do that, statisticians would actually, what they would do is they would take massive data sets. They would analyze these massive data sets by taking random samples from those massive data sets, crunching the numbers, and then predicting what the actual value of that massive data set would be. Right now, it's a new world. Now, we can. What happens is these cloud technicians, if you want to call them, or cloud engineers, right? META students, that some of you guys might be striving in that career path, right? What they do is they build these distributed servers, and these servers now store data in different spaces. And now, let's say you want to take an average of this massive table that's broken up into these different servers, this is what MapReduce and Hadoop do. They will take the averages of the different these different pieces of data broken up, and they will run that analysis at the same time, concurrently. And then they will concurrently take an average of those smaller pieces of data and then bring those results back and give you and apply some mathematics to it to get the overall average. So then that's how now these massive amounts of data are crunched in like almost real time, because it's happening concurrently. It's being broken up. The processing power is being broken up on these data concurrently, and it's happening at the same time. It's wild. All right, so here, because we're using a random sample of data from a larger data set, right, we are not sure, we can't be sure that the answer is correct because it's just an estimate of an unknown data, right? Now here, we're going to use the cofint function, which allows us to see the estimate of the error, right? For example, assume that we use 30% of the data to analyze the rest of the data, right? So let's go ahead and we have the advert table, right? And the advert table, it is very small, but let's go ahead and assume it's a massive table. And we want to go ahead and try to figure out, take a sampling rows of the table and try to figure out what the result of the total table is, right? So here now, I'm going to use a new function called sample, guys. I'm going to use a new function called sample. And do I show you? Yes, I have an example of sample right here, right? And basically, we're going to run this analysis right here. What I'm going to do is I'm going to create a smaller table from advert, and it's going to be randomly like 30%. It's going to be 30% of the table. And then I'm going to use that little table, again, the 30% of the randomly selected rows from advert table, and I'm going to make another linear regression model, right? And the point is, from that linear regression model, I want to see what the intercept and coefficient results are compared to what my actual linear regression model was when I used all the data. You get it? All the data. This, ladies and gentlemen, what I'm trying to show you, I'm trying to basically give you a theoretical understanding of what the science of stats really is. This is what the science of stats really is. The science of stats is taking always a smaller set of data from a larger pool of data where that larger pool of data can't possibly be analyzed because either there is no way to get all the rows of the data, or it's just too large to process. So the way you analyze it is you take a sample of that data, you analyze that sample, and then you let the results of that sample speak for that whole large set of data. That is the heart, that is the very essence of what statistics is. Okay? It is the science of guesstimation, if you will. All right? So let's go ahead and do this example. But before we do that, let me break down what this sample function is and what it's doing for those of you that have never used it before. So what's sample pretty much do? Okay, well, sample just takes random samples from any kind of data container you give it. So let's say we have this vector right here, VV. Right? VV is just the values of 5 to 15. Right? If I place that data container VV with a comma 5, basically I'm saying, hey, randomly choose 5 different values from that vector. All right? And every time you run it, that line of code, you will see you keep getting different results. Right? Let me show you right here. VV equals 5 to 15. Now if I do sample, VV, comma 5, you run it, I get 9, 10, 6, 11, 15. All right, let me do it again. 6, 4, 5, 7, 8. 6, 14, 5, 7, 8. 14, 7, 6, 5, 15. 15, 5, 14, 12, 7, etc., etc., etc. Okay? You see, it just keeps choosing 5 randomly different values from that vector. All right? Now, you saw this other command right here, back here. Set seed in line 1. What's going on there? What is that? All right. Set seed, what that does is when you're doing some sort of analysis, right? When you're doing any kind of analysis that involves randomness, sometimes you want the same random, when you're testing it, you might want to see if it actually works. And to see if it actually works, you might actually want to use the same random numbers over and over again, right? How do you do that? You use this concept called set the seed. Set the seed, right? And in Python, I was just teaching. I was just doing a lecture on scikit-learn, which is a machine learning package in Python. There, they have something called random underscore state. Same concept. Same concept, right? How does this work? Well, let's use you. By the way, you can put any number in that. In this, I put number 7 in there, but you could put 7,000, 1, 22. It doesn't matter, because what happens is whatever number you put in there, somehow mathematically it generates random numbers off that one number, so that anytime you use that number, the same set of random numbers is generated. You see, I don't know if you guys know this, but in the world of mathematics, the science of randomness is the hardest science of mathematics, because in actuality, nothing is random. I'm sorry. Some philosophers will jump down my throat for saying that. Let me restate that. What's in the world of math, in the world of sciences, like there's hardly any kind of randomness, right? It's very difficult to produce something of random work. The way we actually, as a human being, right? You think you can write down, like let's say you take a pencil and paper and you start writing down random numbers, right? You think you're writing down random numbers, when in actuality what's happening is you're actually generating some sort of pattern. Overall, you're generating some pattern if you do it enough. In fact, that's how in this field of forensic accounting, they catch a lot of numbers that are not genuine transactions, because those not genuine transactions will have random results. I'm sorry, not random results. They will have a pattern. They'll have a pattern. Human beings, we always fall into some sort of pattern, even at the subconscious level. In fact, the only type of individual that can truly do random values, anybody want to take a guess, is who? 1 1,000, 2 1,000, 3 1,000. None of you got it right. A psychopath. A psychopath, right, can produce random numbers. Also, a psychopath can produce a perfect circle, when they draw a perfect circle. Fun fact. All right, so set seed, let's use it over here. I'm going to use it now right here. Set.seed. Choose any value you want. I'll choose 7. I run the set seed. I run my sample. Look at the values I get. 15, 8, 6, 5, and 13. All right. I'm going to run set seed 7 again. Look at the values I get. 15, 8, 6, 5, 13. I'm going to run set seed one more time. Look at the values I get. It's the same set of numbers I keep getting. That's what set seed does. It gives you a fixed set of random numbers that you can use in testing some sort of simulation you're doing. And finally, when you're done, when you feel that the testing part is done, then you can truly unleash the model and make it random. If I run this one more time again, boom, it goes back to being random, total random. See that? It has to be done in tandem, setting the seed and then running the sample. So that's basically what I do there. All right, so that's basically what each thing is doing. All right, now let's go ahead and use the sample function to get the random results from the advert table. Now the advert table is, like I said before, we want to get random rows from advert table. We want to get 30% of the advert. We want to get 30% of the. We want to randomly select 30% of the rows from the advert table into a new table called little advert. All right. So how do I do that? Well, okay. First of all, you notice that I'm only selecting the row part over here, right? You notice I'm selecting the row part, and the reason being is because, right? If I show you the advert table right here, if I simply just select the row section and I just typed in the number 1, it would give me the first row. If I typed in the value 10, it would give me the 10th row. Even though the result comes out as 1 over here, this is really the 10th row. This is really the 10th row. You can confirm it by going here and looking at the 10th row. What's the value? 43, 42, 71, 157, 36. Ta-da! Okay? All right, so just like before, that's how data tables works. In fact, I can go in here and I can put in, sorry, falling into Python syntax right here. I can go in there and I could put in random values explicitly. I can choose a 3, I can choose a 5, I could choose a 1, I could choose a 30, a 76, right? Choose all these values. Oh, put a 7 in there, whatever. 2014, perfect. And when I run this, what happens is here, guys, I now get a subtable of 5 rows that is now going to be the 3rd row, the 5th row in this order. The 3rd row, the first row here is the 3rd row, 5th of the original table, the 5th row of the original table, the 1st row of the original table, the 14th row of the original table, the 76th row of the original table. And this is how I'm going to, this logic right here is basically how I'm going to get, I'm going to do random, I'm going to basically take the big table and randomly generate a smaller table from it of a certain percentage of the rows, but I'm going to randomly select those rows, okay? So, okay, now what's going on here? I'm going to use the sample function to do this, right? If you remember, the first parameter of the sample function is what? It's basically the data container. The second parameter is how many values you want to randomly select from that data container. What the heck is this? .n, comma, 0.3 times .n. What's going on there, right? Well, in data tables, they give you this nifty little function, a nifty little term called .n, right? And in data tables, anytime you see dot before something, it's something specific to, like a .n like this, capital N. It's something that's specific to data table, some sort of functionality that's data table puts in there for your use. .n is pretty much doing the same thing as n row, all caps, n row, right? It literally, what .n says is, it gives you the value of how many rows there are in that table. That's basically it. So .n over here is going to represent the number, right? How many rows do we have? We have 172 rows. It literally represents 172 rows. So the dot capital N is basically going to give 172 because there's 172 rows of data. That's the length. So it's literally going to be sample 172. All right, comma. So this is going to be 172. Instead of giving a data container, you're giving the number 172. That'll work too. If I go here and I say sample, and I put the number 10 in here, and I put comma 3. So if I just put a 10 in there and then a comma 3, it understands, okay, by default, it's saying, okay, you want to basically select 3 values from the possible values of 1 to 10. 3 values from the possible values of 1 to 10. So here, this .n over here represents all the rows in advert, which is 172. So it's saying, okay, cool, you want to select from the numbers 1 to 172, okay? And after the comma now, like up here, it's how many of those numbers you want to select. We already said, let's select 30% of the advert table, 30% of the advert table, right? So here now, I'm just doing a little bit of math. I'm literally saying 0.3 times 172, right? Remember, point n over here is going to be 172. 0.3 is 0.3, right? So if I literally do 0.3 times 172, it gives you 51.6, right? What ends up happening is it's going to end up just dropping that 50. It's going to end up just dropping that 0.6, right? So it's just going to take the whole integer number right here, just the 51 part. The 0.6 will be dropped, and so it's going to be literally turned into sample 172, comma. It's going to be interpreted as sample 172, comma 51, and it's just going to give you a bunch of random numbers or random rows, if you will. And these random rows, 51 of them, will become little advert. So that's basically how we take a random sample of a table and create another table that's a random sample of another table. In this case, we're only taking 30%, not the whole 100, right? So let me go ahead and do this. Create my little advert table. Boom, I got a little advert. I click on that, 51 rows. All right, sweet. Now, I'm gonna go ahead and do setting the seed. I don't know why I chose 4510, but whatever, you can choose whatever you want. I'm gonna go ahead, let's copy all this. Oops. All right, I set the seed, and let's fix this up here. All righty, set the seed, create the table. Oh, I already created a table, whatever, I created it again, no biggie. Run the linear regression again on this smaller table. Same linear regression, but on the smaller table. And now I have this new sample model. Look at the intercept and look at the coefficient. All right, look at the intercept and look at the coefficient. All right. Now, my actual value, now here, let's go back to what I was talking about from before, the cofin function. Where are you? Right here, the cofin function, right? That basically will generate the confidence intervals for us. If I simply pass the sample square model, my linear regression model I just made, within the cofin function, right here, here it gives me the actual values, right? But at the same time, let me scroll this up a little bit. Boom. Look what it's giving me now. Here's the actual intercept it calculated. Here is the, in this case, the 95% confidence interval. The 95% confidence interval range for the intercept. Notice this one fits right in there, okay? Here's the coefficient for my sample. Here's the range for that coefficient, okay? And again, the confidence interval is saying that 95, in this case is a 95% confidence interval, 95 times out of 100, 95 times out of 100, you're going to get an intercept that falls within these values. You're going to get a coefficient for marketing total, 95% of the time, that's going to fall within those values. That's what the confidence interval is saying. Now, this is from the sample values. I think it's, okay, it's slightly different than what I calculated. That's fine. This is when I first ran it for the slides. This is my original model. This is my original model. You notice anything? This is the sample data. This was the actual, I mean, for the sake of this sample data, this was the population data from the sample data. This is the regression on the whole thing. Do you notice how even when we just took a sampling, a random sampling, our intercept obviously is different here, in our marketing total, our coefficient's different, but it's about the range. It falls within the range. This falls within the range. And now we're getting to the heart what confidence interval is saying. 95 times out of 100, when we run this when we take a sample and run the regression, okay? Or when we run any kind of statistical analysis, when we take the sample from their big table and run the statistical analysis, 95 times out of 100, we're going to get the intercept value for the whole data. 95 times 100. So 5 times out of 100, we're going to get a score, that a value or a range that will be not here. We're going to get a range that does not encompass this number, 5 times out of 100. Down here, 95 times out of 100, we're going to get a range that encompasses this number. In this case, it worked out perfectly. But there's 5 times out of 100 where we're going to have a range that's going to be outside the scope right here. Either the range is going to be too much or too little. Either the lower bound or the upper bound is not going to capture this. That's what confidence interval is saying. It's talking to the population data. It's saying, okay, 95 times out of 100 or 99 times out of 100, you will have the same value as the population data, but that 1 time 100 or 5 times out of 100, you're not. right? So that's what this range is saying. That goes to the heart. I'm giving this example because this goes to the heart of what statistics is. This not just applies just to linear regression. This applies to everything around stats. That's the whole point of stats and confidence intervals, right? You're trying to use the sampling data, the range of the sampling data, to describe what the answer of that statistic would be in the large mass amount of what we call population data, if we ever theoretically had access to that theoretical data. Here we did. I did an experiment right in front of you guys. All right? So, moving right along. Oops. All right. So, again, this is basically the same concept I just talked about. It shows that if you take 100 different random samples from the advert table, 95% of them will estimate the slope of the marketing total between this value and that value. All right. Again, when I mean marketing total, I mean the actual marketing total. 95% of the time, this value will fall within this range, or that range will encompass the actual whole data set. Okay. Main concept between sampling statistics. All right. Now, here I give a brief example of, and I just wanted to touch on this a little bit because this is actually a big deal, especially in my space, right? There are times when the line assumptions might be violated. In fact, there's a lot of times those line assumptions are violated. Consider an example here, another example here, this data set below. All right, we're going to run a SLR, simple linear regression, to generate the diagnostic plots, all right? So here, I'm going to take this X, and I'm going to take this Y, right? And I'm going to make a new model, and create a table, and we'll plot it, all right? Let me grab this first part. Alrighty, so I created a new model. Now, let me plot this graph. Let me do this. Let me do that. And let me do this. All right, perfect. All right, let me fix this up a little bit. Alrighty, now look at that graph. Okay, now here, if we look at this graph right off the bat, what do you see, guys? It's kind of subtle. Let me see if I make it bigger, you can see it. Is this a linear graph? If I plot the data points, is it linear? All right, let me change the dimension so it's maybe easier for you to see. All right, I'm playing with this too much. But anyway, as you can see, oh, what if I go like this? As you can see, oh yeah, there we go. This might be easier to see this way. Right? The data, it kind of curves, right? The data points are kind of curving. There's a little convexity here. All right? Now, all right, right there. Now, right, let's look at let's run a couple tests right here. Right, let's do a couple of the normality tests. Well, one, is this linear? Okay, it's kind of curved, but fine. If you want to say it's linear, whatever. Let's move on to the next step. Is it independence? Let's assume it's independent. Let's go ahead, skip that, and go straight to normality. How do we test normality? Remember, we do histogram. We do a histogram for the residuals, the error terms, and we also do the normality test. I'm sorry, the QQ plot test, right? So let's do one. Let's do the histogram one first, guys. Oh, let's first create a table. Again, let me just copy and paste this. It'll be faster. All right. First, we create another sample table. I already have a SAMP. I guess I already have a SAMP DT table. I'll go ahead and use it. Why not? Right, I have it from before. I just added to it, guys. I just simply added the residuals to it. And now let me go ahead and graph this. Oof. All right, let me do plus over here. All right, sweet. All right, and fix this. All right, normality. Is this a normal distribution? Tis not a normal distribution, guys. It's not a normal distribution. It's failing the normality test. Let's look at the QQ plot. You guys remember how we did that? Oh, I didn't put the code for the QQ plot. I'll do it right here for you guys again. Remember, I have it from above. You take the slight difference will be that instead of saying X, you will say sample. Instead of the normal graphs, you start using the ones that have stat before it. Okay, so I'll put samp dt, sample equals res, very good. Let me run it. And look what we see. Remember how this is supposed to look, guys? It's supposed to be a straight line. The points are supposed to be on the line. You barely have any points on the line. We don't have any points in the first place, but we barely have any points in the line. So from the histogram and this, it's not really showing normality in any way, right? And finally, we do our equivariance test. The equivariance, remember the equivariance, we're plotting the residuals, the errors, against the predicted values. All right, I'm gonna use a SAMP DT table again. I'll just add the fitted values to it. Again, fitted values in my regression model, that's the predicted y's. That's the predicted y's. That's what it's called, fitted values. All right, let me fix this again. Boom. 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 And the boom. All right, so let me graph this now. All right, look at that. Okay, does this look like a does this look like a situation where we have, I don't know, no patterns? We have a clear pattern here. Look at that. We have a clear pattern right here, right? Is this showing a scenario where the y is not, even though, look, check it out, even though we do have a horizontal line going like this, but does it look like there's no pattern here? Is there scattered plots going across the graph? There's not. You have a clear pattern in the residuals versus the predicted values. It's failing the equivariance test. All right, this data is failing the diagnostic graphs or the line assumptions. We can't build a linear regression model off this, right? So what do? The first plot, fine, it shows linearity, but the other graphs do show violations of the normality and equivariance properties. This data is simulated, right? In essence, that y, if you guys haven't realized it, is a square root of the x. This is how data transformation comes into play when you have scenarios like this. Now, obviously, this is a fake scenario, right? It's a very blatant scenario, but this is what they mean by data transformations. A lot of times, you have data that fails the tests. So what a lot of statisticians do is that they will go ahead and manipulate and transform the data so that when it runs the line regression, the line assumptions, or diagnostic graphs in Tableau, it will not fail. Those assumptions, those line tests will not fail. So in our scenario, right, that y is the square root of x. So let's transform it, right? There you go. So first things first, I'm creating a new vector called y2, which is going to be y squared. All right? Then I'm going to, well, let me clean this up a little bit. I'm going to create a new linear regression model, this time with y2 and x, where y2 is the independent variable and x is the independent variable. Run that. I create a new table, sampd2, which is going to be x and y2. And now I'm going to do some graphs, right? Here I'm going to get the, actually before I do the graphs, let me put the residuals in that table and the predicted values in that table. So now I have everything in that table to do the graphs I need and to do my line assumptions. All right. Now I will literally just keep things simple. I'm going to go ahead and just grab this stuff right here, these graphs right here, because I have it already. Copy it, paste it. We'll do one by one. All right. The only difference is I'm changing the table from SAMP2 to SAMPD2. I believe the names are still the same. X, Y, no, now it's Y2. So Y is Y2. And now let me graph this. Ah, look at that. Is it linear? It's much linear. That wasn't really the problem last time, but let's go ahead and move on to the next test. Let's do the histogram test now, guys. All right. So this is the one for the histogram. I'm using the new table. Is it normality? Normality is still, Let me go ahead and make the bins slightly more smaller to see if it looks kind of normal. You got that big one in the middle. You got the large 0 right there. So let me do this, make it 3. Oh, no, not bins. I want bin width. I actually want bins larger. So let's do 25 bins. Right, I just don't have that much data, but look, check it out. Right, it's not really a normal distribution. It's more like a fat tail than anything else. But you do have this hump in the middle. More importantly, you have this concentration of 0 residuals in the middle, right? And it's somewhat, I guess, somewhat equally weighted around the sides, right? Let's look at the QQ plot, right? And here's the QQ plot. Again, SAMPD2, the new table we created. All right, and looks okay. Looks okay. It's not spectacular, but I guess it's still better than the other one we had. It's not spectacular, but it's still better than the other one we had. All right. And now finally, this test right here. Let's do that. SAMPD2. Let's compare the predicted to Y residuals. Okay. This is much better now. This is much better, right? Now it's, I mean, now you have like, it still looks like you have a lot, like a circle going like that, but now you have a little more randomness here. Now you have a little more randomness as opposed to that nice little curve we had going before. All right. And this is why and how basically we create these new kind of values, or we do these kind of transformations. It's so that the line assumptions won't be violated, right? Here's a graph right here in front of you. We just ran from before, right? And again, this is something that it is data wrangling, but it's data wrangling with a purpose, right? You're applying some sort of transformations to the data so that the assumptions and the violations that are preventing you from using a linear regression model, you can satisfy them and start and create some sort of linear regression model. All right, now Let's jump into multiple regression. All right, so that was your linear regression. Now let's do some little multiple regression action here. Okay, so here I'm going to run the same, I'll use the same function again, but this time, people, I'm using more than one independent variable. There we go. Can you see this? Let me scroll over. All right. Now look what happens. Knocked out my headset. So again, revenues is our dependent variable. It's to the left of the tilde. Look what we do now to the right of the tilde. I got now Google AdWords, Facebook, and Twitter. Look how we separate those independent variables. We use the plus symbol. We use the plus symbol. All right. No, it's not. Math is not going on here. It's literally that's the syntax for saying, hey, I'm using this column and this column and this column as my independent variables in this linear regression model. And obviously, advert is my. It's going to be my. It's my table as well. So go ahead. I'll go ahead and run this. And now I have, it's very simple. I have model 2. That easy. All right. That easy. All right. Now, if you remember, let's go ahead and do a quick sanity check on linearity. Ooh. Figure margin. Oh, sorry. Here we go. Now I could do this. It's basically throwing an error because it's like, hey, the window's so small. All right, so if you remember, this is the one for multiple regressions, right? And we found, hey, just as a reminder, against revenues, we're doing this against revenues, right? Yes. Against revenues, Google AdWords, pretty good. Facebook, it's okay. Twitter, it's horrible. All right. Now let's do the rest of the analysis with that in mind. Linearity for at least those two, at least for Google AdWords and Facebook, they seem to hold. Not so much for Twitter. Okay. Now let's go ahead and do our other multiple regression tests. All right, let's go ahead. I skipped a step about where I create the RESDF2 table, but we'll do it right here. All right, first things first, guys. I want to get our error residuals. Right, I need the error residuals. I graph those first. So I'll get res equals, what's the name of my model? Model 2. Dollar, where's my residuals? They're right there. All right. And you know what? Let's go ahead and get our predicted column also. Let's do it all in one shot because we're going to need that anyway. So let me scroll over here. And so my predicted column is going to be equals, again, model 2. And which one is the predicted y's, guys? Fitted.values. All right. That looks like it worked. Okay, perfect. Okay, so now we can do the graphs again. We'll do the graphs again. Again, let me, I think I could just copy and paste it from above. Just test my normality. Oh, just test my normality. Let me grab it. All right, let's run this. How much did I do it for? I did it 10 bins. All right, I'll do 10 bins here again. Getting the error because I need more space. Guys, listen, I was doing a little bit of error in my graph. So if sometimes you're gonna get these weird errors right here, this one right here, call graphics. When you get something like that, just type in dev.off like this. I don't know why it happens. Sometimes it happens with ggplot, and it'll just reset ggplot, and then you can run your function graphs. So I did that, and I run my graph now right here. And you see this graph right here. And as you can see, is it normally distributed? I mean, this part it looks normally distributed, and it kind of just shoots up over here, right? But this part is kind of normally distributed. Over here, okay, so here, and then here's a 0. So again, 0 is large, so we like that. And then it goes down slowly. Then all of a sudden we have these set of numbers right here, which is problematic. So we do have some sort of problem. Like one side is kind of normally distributed. The other one's not really. Let's look at the QQ plot. All right, I have that right here. All right, not bad. Okay, so excellent. So again, like last time, we have the numbers around the lines. In the middle, it's perfect, right? Again, around zeros. And just like before, it kind of tapers off to the side, off that line. So it looks like we do have some normality issues in some part of the data, right? In some part of the data. Okay, let's continuing on. We now have to do the, what's the next test, guys? Equal variance. Let's go ahead and graph that now. I have that as well right here. Where'd you go? Where'd you go? It's right here. All right. And look at that. So this is nicely scattered. Look at that, it's nicely scattered. Yeah, I do have a little more scattering on top than you do on bottom, but I mean, at least you don't have those patterns from like before that we saw, right? So it's nicely scattered. All right, let's look at the summary. If you guys remember how the summary works. And what do we call this? Model 2. Okay, okay. All right, here's the results right here. Let's look at this, guys. Right, here's your residuals. Okay, very nice. Here's my estimate, my intercept, my Google AdWords, my Facebook, and my Twitter. Okay. Now let's look at what this is saying. Remember, the units is $1,000. The units is $1,000. All right. Before we jump into the F test, 29. If I don't spend any money on any of this advertising, then I will generate a revenue of $29,545. Okay. Here's my standard error, my standard deviation of the errors estimating this. And I have a t-value of 55.38. Again, it's very high. The p-score is very low. Like that's virtually 0. So this is statistically significant. Okay, I'll take it. Google AdWords is now 0.048. So basically what this is saying, for every $1,000 I spend on Google AdWords, for every $1,000 I spend on Google AdWords, I'm contributing $48.38 to my revenue. Right? 1, 2, 3. $48.38. All right. Here's your standard error. It's pretty low. T-value, again, is very high. The p-value is very low. It is statistically significant. Okay, sounds good. Here's the estimate for Facebook. Here's the standard error. So wait, first of all, look at the value for the coefficient versus AdWords. For every $1,000 of money I spend on Facebook, I'm now going to get $197 in added revenue. You see that? $197 in added revenue as opposed to $48. That's interesting. Let's look at our t-value. Okay, t-value is still big, and the p-value is still small, very small. That is statistically significant. Twitter is saying now for every every $1,000 I spend, I get $3. About $4 in revenue. Standard error. The t-value is, let's look at this, 0.47. The standard error is larger than the estimate. I got a t-value of 0.47. That's a small t-value. What's the probability of that? 0.639. 0.639. What that means is that is all the way here. 0.639 means that's a large probability, right? That means somewhere over here. That's somewhere over here, right? If we're looking this way, because this is 50%. So here, somewhere over here, it's dead center in the middle. What is that saying? That's saying that t-value could be, this value right here, could be actually completely random. This t-value is not large enough for us to say, hey, that is a statistically significant value. It's not. And before, remember we said visually, keep an eye on Twitter? It looks like a general cloud? Yeah. Twitter's not statistically, it's not statistically significant. It's not contributing anything, really. It's not statistically significant. It does not belong in this model. It's not contributing anything of value or worth into our actual model, right? And you see this, we saw that visually, now we see it quantitatively. You can go into management now and say, hey guys, look, based on these scores, what Twitter's contributing in terms of what Twitter is quantifying to our revenue, it's pure random. I mean, it's just noise. It's not really contributing anything from a statistically significant place to our revenue. You could show them the cute graph, and you could show them the values and say, hey, I mean, we should, and you're going to pretty much give your advice. My advice is, let's go ahead, explore continue our digital marketing strategy, but now let's cut Twitter out. Let's take the money we were giving to Twitter and now give it to Google, Facebook, Google AdWords, and Facebook, and see what happens there, right? So that's basically, we see that point blank now at this point. All right, now we talked about these, and I said, listen, we got something else going down here. We got something called, by the way, notice the degrees of freedom went down. Why? Degrees of freedom went down because originally, again, we had 172 rows of data. We have now 3, but now we do -3 because now we have 3 independent values, and then we do -1 for the intercept, right? That's basically -4, so it comes down to 168 degrees of freedom. All right, now, finally now, let's talk about two things. Let's talk about what the F statistic is and what the adjusted R squared is, right? What are the F statistics? The F test, so we did the T test on the individual values, right? We did the T test on the individual values pretty much. We like this, we don't like this. But the F test, before you even look at those columns, you got to ask yourself, okay, what about the overall model? The F test is for the overall significance of the model, right? It's going to show you if there's a linear relationship between all of the X variables considered together, collectively, and Y. That's what the F test is used for, right? You calculate an F test statistic, and you're testing a certain hypothesis. Okay, you're testing a certain hypothesis. Now, I skipped this part, but the T test is also testing a certain hypothesis. What is the T test testing? The T test is testing whether the intercept is 0, Google AdWords is truly 0, the Facebook coefficient is 0, the Twitter coefficient is 0. The T test is testing whether these values are in actuality 0. And if the T value in the T test is not further away from the middle, like we just said, with a small p-value, right, it's really far away, then that's saying, hey, you know what? We have enough data to reject the null hypothesis. The null hypothesis is basically saying, hey, this thing is just truly 0. These values are just rubbish. These values are just rubbish. Now, I just said something. I said the null hypothesis and the alternative hypothesis. Well, now I'm saying it. Statistics, when you're doing analysis, it's all about hypothesis testing. Do you guys remember this from stats? Hopefully you do. This will be a review, right? Specifically, linear regression. You are testing different hypotheses. The main hypothesis that you are testing is the null and the alternative, and it's real easy here. The null hypothesis is that your coefficients are all truly 0. There is no linear relationship between these coefficient values, basically between your independent values and your dependent value, what you're trying to predict. Between your predictors and what you're trying to predict, there is no relationship. There is no linear relationship. These are all actually zero. That's what the hypothesis test is saying. Okay? Now, for the individual t-test, it basically does it one-on-one. It says, for this test, it's saying, oh, the intercept is truly zero. For this test, it's saying, oh, this coefficient is truly zero. The null hypothesis is saying it's truly zero, and we have to find enough evidence to reject the null hypothesis. Same thing with this one, same thing with this one. But the F test, look at it. It's doing it all at once. It's saying, hey, all the coefficients are zero. All of them are zero. Okay? There's no linear relationship between any and all of them and the value we're trying to predict. That's what H0 stands for. This is why all these are equal and they're zero. The alternative test. See, we have to either accept or reject one of these tests, right? The alternative is basically saying, hey, at least one of these coefficients, not all, just at least one is not zero. It's statistically significant. So at least one of these coefficients has some sort of linear relationship with what we're trying to predict. All right? And this is different again with the alternative for these tests as well. The alternative is literally going to be, the alternative would be, oh, Google AdWords is statistically significant, or it's going to be the alternative for Facebook is Facebook's coefficient is statistically significant, and Twitter's will be also, hey, this is statistically significant as well. Okay? Whereas the F test is saying, no. Either the null hypothesis, they're all zero, truly zero, true zero, or the alternative, at least one is not true zero. So at least one has some sort of real linear relationship with the model. All right? This is how an F distribution looks like. It's one-sided. It's one-sided. Unlike the normal distribution where you have two tails, here you just have one. And just like how you were testing the 95% confidence interval, one tail is 2.5, the other one's 2.5 for a total of 5%. Or if you're doing a 99% confidence interval, one side would be 0.005 and the other side would be 0.005. Here, if you're doing a 95% confidence interval, this is 0.05. This region is 0.05, right? And the way this works is we have to find the critical value based on degrees of freedom. We basically find where this line is. What is this F value? And then from our graph, we have to get our actual F value from our actual model and see if it falls in here. If it falls in the yellow region, then what's going to happen? So for example, like I just gave this random 3.855 example, but if it falls in this yellow region, we then reject the null hypothesis. By rejecting the null hypothesis, we are claiming that, hey, at least one of these coefficients is actually, maybe it's all of them, but we are saying at least one of them has a linear relationship to the predicted value or the dependent value. If the F value falls to this side of the F critical value that we have to calculate, then guess what? We fail to reject the null hypothesis. We fail to reject the null hypothesis. And so basically we're saying, well, look, so we don't have enough evidence to say, we don't have enough evidence. We don't have any evidence that says that all the coefficients for the independent variables are zero. Therefore, this model is rubbish. This model is rubbish because we didn't find any evidence saying that, hey, we should not reject this. We should not reject the null hypothesis, or that there is something to this model. We didn't find any evidence saying there's something to this model. You notice that inherently we're skeptical. We're skeptical. That's the way science works. We are skeptics, right? And we are trying to always look for evidence to reject our skepticism. Here we are skeptical that the model we ran is indeed statistically significant, or that the model we ran actually has coefficients that actually do have some sort of linear relationship to the dependent variable, or the variable we're trying to predict. right? And we are looking for evidence to tell us, hey, reject your skepticism. You should reject your skepticism and at least accept one of these independent variables to having some sort of linear relationship. All right? So how do I go about getting my F critical value, right? Well, we have a function called QF. The first parameter is the confidence interval you want. If you want 95%, take 0.95. You want 99%, take 0.99. You want 90%, take 0.9, right? The other two parameters, this now function has two sets of degrees of freedom. The first degrees of freedom, the second degrees of freedom, all right? df1 and df2, all right? Now, df1 is always going to be the smaller set of degrees of freedom than df2. That's just how it is. It's very easy what df1 is. df1 is simply the number of independent values you're using. We're using 3. Facebook, Google AdWords, and Twitter. Done. df1 is 3. 3 independent variables, df1 is 3. df2 then is what? df2 is our same formula from before. The number of data we're using, 172, minus the amount of independent columns we're using, 3, minus 1 for the intercept, which comes out to 168. It's that simple. df2 is always that formula. df1 is always the number of independent variables. And now, given these two values, let me go ahead and just copy this in. I get a value of 2.65839. That is my F critical region. That 2.65839, let's see, I have a slide for it. No, I don't have a slide for it. That would go here. So, and that would have the number 2.65839 right here. They would go right here, and that would have the number 2.65389. Excellent. So we drew the line in the sand at a 95% confidence. Now, what is my F statistic for this example? My God, it's 339.8. Where does that fall on this graph? If this is 2 point some blah, 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 339 is all the way here. It's all the way down here. Flies off the screen. We are way in the reject region. Way in the reject region. So we say we reject the null hypothesis. We reject the null hypothesis that they're all 0. And this means that we are saying, listen, at least this F value is way too big to say these are all 0. There's at least one of these coefficients that is truly has a linear relationship to the predicted value. And that's when you really go, we kind of went backwards, and that's when you really go to the t-test like we do here, and we see that. We have a t-value here that makes us reject the null hypothesis for Google AdWords. We have a t-test here that makes us reject the null hypothesis for Facebook. But we got a t-test here that fails. Fails. We fail to reject the null hypothesis here for Twitter. Twitter's out. Twitter's out. So from here, we can see it's Google AdWords and Facebook. We would rerun this model with just Google AdWords and Facebook. Okay? So that's how this pretty much works. That's how much this pretty much works. So we'd rerun the model, and we would drop Twitter. Now here, now let's talk about the adjusted R-square. Right here, the adjusted R-squared that says it's 0.856. Okay, what is that? The adjusted R-squared value shows how much the variation is dependent, how much variation in the dependent variable is explained by the variation in the independent variables. It's a good explanation. What they like to say, it's a good explanation of fit. Some people like actually looking at the residual standard error, or the overall residual standard error, right? Some people actually like that, comparing that number. But the adjusted R-squared as well as another statistic or measure of goodness of fit of the overall model. Okay? Now, this is important. What this is saying is that when you have this 0.856 here, right, just adjusted R-squared 0.856, what this is saying is that 0.856 of the variation that we see in the predicted value, in the revenues, okay? 0.856, so 85.6% of the variation we see in that data, 85.6% of it is explained by these data, by these columns of data. All right, let me say it again. So the movement and change we see in the data of revenues, okay? The change we see in the revenues, 85.6% of that is being explained by the change in this data, in the change in the independent columns data. That is what R squared is talking about. R squared is saying how much percentage of the change in the dependent variable is explained by the percent changes in the independent variables. And in this case, 85.6%, that's a large percentage of that data is being explained by our independent variables. That's a pretty that's a pretty good fit, right? And from here, you can ask yourself, okay, if that's the case, then what's the other 14%? Where's the other 15, 14% being explained by? Maybe there's another column we're missing. You see? That would make us say, question, okay, what other factor is there that we're not taking into account? Maybe it's another column in our data table, or maybe it's another type of data we don't have access to that we haven't even thought about, right? That's where that question arises from. If we had an adjusted R squared that was just 10%, 10%, that's saying that, hey, guys, only 10% of the change in the revenues is being predicted by the change in Google AdWords, Facebook, and Twitter. So that would tell you, okay, if that's the case, that's not really a good fit. The 90% of the change is being explained by something else. What? That's where you go out and get other columns and try other kind of regression models, right? That's basically where it all comes from, okay? So we can end our review of regression here. And again, I wanted to focus basically on how you do it in R, how you do the different graphs, and I didn't want to really go on what this all means, but you guys already know what this all means, so this should be all a review, right? And so this ends our lecture 4. All right. I'll see you guys in Q&A. Have a good week. All right, bye.